is 5.6 and squared. The idea is, well, we know how we have some curve, some f of x, and we know how to find the area underneath this curve. And if there were another function, some g of x, and we wanted to find the area between these curves, it should be kind of obvious. Between, let's say, points A and B. Well, f of x is all this area. G of x is down here. So if you were just to take the integral from a to b and subtract the integral from a to b of g of x, that would give you the area. Area B, area between. So that's pretty straightforward. Now, this of course is positive area, and this is positive area, so there's nothing particularly ambiguous about this. You might wonder, well, what happens in that place? What happens if of x is down below, g of x is down below? Well, you might worry about that. You might think, how do I, is there something special I have to do? So, let's take this, equation here. Think about it for a second. What if I were to move the axis down here, some distance I'm going to call C? What would happen? We'll bring here. Well, this would become f of x plus c. F of x plus c, and this would become g of x plus c also. Pardon my not being in a big rush. We're not in a big rush today. I'm going to pass it over. So what happens here? Well, this is a to b f of x. A to b of c minus a to b of b of x minus integral a to b of c. Well, clearly these cancel. So what that tells you is it doesn't really matter whether these functions are above or below the axis. You still get the same value by subtracting the integral of f minus 3. Oh. Okay. That takes care of a lot of what we're interested in. There is one more complication that we want to look at. Is what happens if these functions overlap in some manner? Well, we saw something like this before. We saw the situation where you had some function and maybe across the axis, and normally this would be positive area, negative area, positive area, but you really wanted just the absolute value. So instead of the integral of f of x, you take the absolute value. That's kind of what we want to do here. We want to take the integral of f of x minus p of x. And we want to know how to evaluate that. We should put a dx here. Well, in order to do this, assuming this is f of x, this will be positive area, this will be negative, this will be positive. So we're going to need to find these points. We just call them C and D. So this will become the integral from AC of f of x minus p of x minus, since this will be negative area, from C to D, f of x minus p of x. And then from here on, from D to B, it'll just be positive f of x minus d of x. All right. So how does that work out in real terms? So we're given a problem, y equals x squared, and y equals, we call this f of x, if you like, and y equals 2x minus x squared. This could be our p of x. Might be a good idea to get a look at what this actually looks like. Y equals x squared is pretty easy. That's just our parabola. If I factor this, I get x 2 minus x. So this is a parabola with intersects the x-axis at 0 and 2. But because we have a negative x squared here, it's upside down. So it's going to look something like this. So how do we go about finding these 2 points here? Oh, where do we want to, I guess this particular example, they don't give you any limits, they assume you're going to find them. And if you look at this picture, there's only one place where there's area between them. So this is the area we're looking for. So how do we do this? Well, to find these 2 points, we can set f of x equal to g of x, or x squared equals 2x minus x squared. So we end up with 2x squared minus 2x equals 0, or x times x minus 1 equals 0. That is to say, this is 0 where they intersect and 1. From there, our job is pretty easy. We just want to find that integral from 0 to 1 of x squared minus 2x minus x squared, which should be straightforward. We have 2x squared again is 2x, so the antiderivative is x cubed over 2x cubed over 3 minus x squared. So it's 2/3 minus 1, negative 1/3. But of course, that just means I subtracted the wrong one. We just want the absolute value, which is 1/3. Try one more before we move on to something a little more difficult. By the way, does anyone have a TI calculator here? Okay. I should have brought one. Okay, again, a simple problem. Y equals e to the x, which again has to be f of x, and y equals x. Again, it always helps to take a look at what this might look like. We have a little piece of area here we want to find between the two. I guess you can see this should be f of x, right? This should be my g of x. So again, we have to find these 2 points here. So what we really want is the x equals x. Find that. Oh. Well, problem. And it looks like it's done incorrectly. Oh, maybe because I'm wrong about this. I think I'm gonna see if I can't take a look. That's one of the nice features we have today is we don't have to guess a lot of the time. Something is okay, so, aha. So my original intuition was wrong, and my intuition that I was wrong was right. These they don't cross. And in fact, the problem states find the area bounded by these two functions on the interval 0 to 1. So this is wrong. And we're just asked to pick between this point 0 and 1. Okay, so again, as I pointed out, I pointed out incorrectly, this function is going to be the greater. So it'll be e to the x minus x from 0 to 1. This is a pretty easy problem. It's e to the x minus x squared over 2 from 0 to 1. So it's just going to be e to the e minus a half. And that's going to be this area between these two curves. All right, any questions about this? It's pretty straightforward. Let's see how we could enhance this if you have more than one function on different parts of the interval. We just have to piece it together like building blocks. All right, so I mentioned we might have a somewhat harder problem to do. Harder in that you might not have a straightforward way to find the limits. So let's take a look at a more strenuous problem. Y equals x over the square root of x squared plus 1, and y equals x to the 4th minus x. And since I'm all warmed up, I'm just going to get a visual on that. Function and x to the 4th minus x. Okay, well, that's pretty. So we're interested in this here. We can see right away that one of the limits is going to be 0, and now we have this problem of finding the other limit. So how would we find this other limit? Well, we have to set x to the fourth minus 4 equal to x over square root of x squared plus 1. Now, it could be that we want an exact answer, in which case, now I have to start doing some algebra and find out what values x could have here. But as an old, yes?
I think it's x to the fourth minus x, not 4. That's
Thank you. Yes. Yes, thank you. But if we're just looking for an approximate answer, we have a nice tool here that I'm hoping, was it Emily? Did you have the HP calculator? You have the HP? No? Who has an HP calculator here? Anyone? No, I'm gonna have to, well, that's okay. We've got Desmos. Oh, that's nice. It's just gonna tell me that the point is 1.181. So I'm just kind of do my little drawing here. So this becomes the integral of, which of these is the, doesn't really matter. I can just always find the opposite at the end, but looks like it's got to be this one. So the integral of x over the square root of x squared plus 1 minus x to the fourth minus x dx from 0 to 1.18 approximately. Anyone remember how we would find the antiderivative of this expression, x over square root of x squared plus 1? Okay. Looks like a substitution, doesn't it? Might want to say u equals x squared plus 1. And then du is equal to 2x dx. I guess I should separate this out. This is integral from 0 to 1.181. X over the square root of x squared plus 1 plus the integral from 0 to 1.181 x to the fourth. No, this is a minus x dx. Well, that would mean du over 2 is equal to x dx. That's what I have over here. I'm going to erase these for right now because these are with respect to x, and we're going to switch this over to u. So this becomes what? It becomes du over 2, 1 over the square root of u. All right. A derivative of 1 over the square root of 2. That's just reverse power rule, right? U to the negative 1/2. So it's going to be what? U to the 1/2 over 1/2. Times 2. Oh, no, times 1/2. So U to the 1/2 is what? Square root of x squared plus 1. Okay, that, now we can put the limits back. That's this part. Now we have x to the 5th over 5 minus x squared over 2. Again, from 0 to 1.181. So let's just get some, we don't have to take this to the end, but this is square root of 181 plus 1. That. Minus 1. That's our first piece here. And then we have to subtract 1.181 to the 5th over 5 minus 1.181 squared over 2, and the rest is 0. So this obviously is a calculator calculation. No, it's fine. This is how the book does it. I think to myself, the calculator will score me wise. This is this odd place we're at in the history of teaching calculus. That's it for finding the area between curves. I'm going to go ahead and take the break a few minutes early, and we'll come back and we'll look at something else.
Yeah. I need to take that.
The next step for this class this afternoon, or this morning, we take you on a little journey. Maybe it'll be entertaining, hopefully. That's my goal. Purpose is not to frighten you and worry you about the exams. Just, you'll see right away this is off schedule, but I think I want to start where all of you might be. So let me ask this question. Does anyone here not recall looking at something in pre-calc called a vector? Does anyone not recall? Okay, so yeah, that's good enough. That's good enough. So a vector, we probably got presented as kind of like an arrow, and it has some kind of, call it V, and it has some kind of length, which I might call the magnitude of V, and relative to some set of axes, has some angle. This is in 2 dimensions. So there are things you can do with vectors. You can take 2 vectors and you can add them, kind of line up, the starting point and the end points. And you get a new vector, u plus v. You can take a vector and you can multiply it by some number. So I'll take v and multiply it by 2. Well, that's just adding another v vector. We get 2v. And we can also multiply it by a negative number. We have some v. We multiply it by -1, we just get a vector going in the opposite direction. So this is the kind of the basic of the math of 2-dimensional vectors. And these are really handy. If you're taking a physics class, these can represent a number of things. They can represent the distance on a map. You measure a distance over time. That would be derivative of distance over time. You can get vector, which is the velocity. And if you, again, find the derivative of the velocity, you find a vector, which is the acceleration. And all these quantities can be represented by these called pointing line vectors, and you can add them up. There's some interesting consequences. So, for example, well, I guess if you have, we'll just say your little toy airplane connected to a string and it's flying around in a circle. Right? It has some radius. Well, at any given moment, its velocity is in this direction, but its acceleration is towards the center. You've got a string and it's pulling it. And as it moves around, the acceleration moves around, except a little out of phase. And if you were to take, well, we haven't talked about it, but if you were to take the component of the velocity in one direction, like the vertical direction or the horizontal, you would get one of our sinusoidal, sine or cosine. And the acceleration would be, again, one of these sinusoidal motion guys, except a little out of phase. So vectors are pretty useful. There's one more thing about vectors I want to point out before I go off the wall entirely. Because of this feature of being able to add vectors and multiply them, we could start with two particular vectors. We call them I and j. And I is a vector along the x-axis of length 1. So I guess, is length 1. And along the y-axis, we have j, which gives a length 1. Then we can pretty much make up any vector we want. We have some vector here, we can break it up into components. So this will be some number a times I, and this will be some number b times j. And our vector, whatever vector you come up with, can be expressed this way. And we call that a linear combination. This is a linear combination of vectors making up a vector. I don't want to push my luck here, but you can see without too much effort, I can have like a z-axis, and I have like a k vector, and then I could really make up a vector in the room. So this idea that I have an object, I call it a vector, I can add it, I can subtract it, I can multiply it, and I can add them up in linear combinations like this. We give that a name in math, we call that a vector space. Should any of you be interested in engineering, you at some point will go on and take a class they're going to call linear algebra. And it involves the study of vector spaces and transformations of vector spaces. Now, the reason I kind of bring this up, just by maybe a smile or a show of hands, I suppose some of you are familiar with this whole thing. You may have seen this, remember it from pre-calculus. But one thing that tends to get cemented in students' minds is that these vectors are, pointing arrows. I mean, forgetting the fact that, sure, the pointing arrow makes most sense if you're talking about distance. Right? You want to go from point A to point B, right? You go various ways. You go the shortcut. But they seem to work with velocities too. If I'm on a train moving this way and I walk sideways across the train, someone outside looking diagonally. But again, this idea is kind of cemented at the vertical pointing arrows. And to mathematicians, this is not the case. We told you what a vector is. It's this thing. We don't know what it is, but it's this thing that you can do these things with it. And there's some rules, and we call it a vector space. We don't really care what the vectors are. They could be something different. So this is kind of my 10-minute introduction to linear algebra. For those of you who go on, you'll learn a lot of interesting things. But now I want to go off in a different direction. So I think to separate the two, I'll stand over by this board. So there may be some of you going on in science, maybe even physics. And if you study chemistry or bio, you're going to have physics. And in physics, mathematics is really at the heart of what we do. There's some things about the real world we bring in, and then we look at how math can help us. And one very simple thing you look at in physics is you put kind of a weight on a spring, and this weight, there's a gravitational force involved, right? Which itself is a vector. And if you just let it sit there, it doesn't move. But if you pull it, it starts to go up and down. And why is that? Well, you've got a spring here that itself is exerting a force upwards, and gravity pulling it down. It's not moving, they're equal. Gravity doesn't change any. Gravity on the object's pretty much always the same. So what's happening is the force of the spring is varying. And it varies with something that's called Hooke's law. It's just it's not an embedded feature of the universe. It's just how a lot of things act. It's called Hooke's law. And the basic idea is that the force depends on, we're just going to call this the x-axis for the moment. It depends on the displacement. So at what we'll call 0, the force is exactly the force of gravity. F spring minus F gravity equals 0. But as you pull it down, the force increases, and as you pull it up, it decreases. And Hooke's law tells you that we'll call this, F delta, that f delta is equal to negative kx. That is, it's in the opposite direction of the displacement, and it's, there's some constant involved that depends on what units you're using. All right, so what do we got here? We've got some force equals some negative constant times displacement. And what is F? Now, anybody who's run into physics in high school knows that F equals ma. M is just a mass, it's the mass of this weight. A, well, we know what A is. A is the second derivative in time, acceleration. X squared dt squared x dt squared. So let's write that down. D squared x dt squared. All right, so now we have something new. Now we have an equation, but it involves a derivative. And if you're an engineer or a physicist, maybe if you're an econ major, you're going to run into this. This is called a differential equation. And I'm not going to bother solving this one. I'm just going to point out that the solution looks something like, x equals some constant times sine of other constant t plus e cosine omega t. Either a or b could be 0 depending upon when you start the thing. This just kind of moves up and down like a sine wave. Right. So again, super quick 10-minute introduction to differential equations. All this subject matter is just right there, right above you. You've got all the background for it. You just have to sign up for a math course, spend a semester learning about it. I'm going to jump ahead a little. I'm just going to put up a differential equation for you. I guess okay. There we go. All right. So I don't really know if this comes from any physical system, but it's an example, and we're gonna solve it. First of all, what does solving a differential equation mean? Right? Y here is a function. I've got the derivative of y and the second derivative of y, and I want their sum to be 0. And that looks like a difficult job. I don't necessarily expect to get one function. It might be, like when we do integration, we might get a family of functions. We'll just have to wait and see. So to solve this, we do this is a simple linear homogeneous differential equation. What those things mean doesn't matter. But the way we solve this is kind of a trick. We look at this and we think, well, we're going to have to add these together, and there's a function involved and its derivative. It looks like it's going to get messy. we had like x squared, well, derivative of x squared is an x, the derivative of that is just a constant, and how are we going to get that to always equal 0? But we do know of a function that's really useful in this context, which is e to the x, or rather I'm going to give us a little room here. I'm going to put some constants in. Y equals e to the ax. And I'm just going to propose this as a possible solution. Get us through here. So let's see. Y double prime equals ab e to the ax. No, that's y prime. Y double prime equals a squared b e to the ax. I want to plug these in. A squared b e to the ax plus 4 a b e to the ax plus 3 e to the ax equals 0. All right. Looks kind of complicated, but we know that the exponential function is never 0. So we can divide it out. So we get a squared b plus 4b plus 3b equals 0. Oh, and that b constant, it doesn't really matter either. A squared plus 4a plus 3, 0. Ah. Now we're back in high school, right? Now we could solve that. What do we do? A plus 3 plus a plus 1 equals 0. So a can equal minus 3, or a can equal minus 1. Well, I go back to my original equation. I'll just take one of these. A equals b to the minus x. If I plug this in, we know I'm going to get 0. So we've solved this differential equation. I also can plug in minus 3. And I've got some room here too. Like maybe the problem has some other constraint. I have some physical thing going on, but I'm shooting a missile off, and I get this equation, and I'm trying to solve it. But the missile started somewhere. I hate that example. East Loving University talking about, well, maybe we're going to Mars. That's it. It's a rocket going to Mars. All right. But well, we want to. Actually, I want to say B. I don't want to say B here because that implies it's the same number. They could be different numbers. So I have this object here, and this is a solution, but I can multiply it by some number, and I still have a solution. And I have another solution, and we could go through the process. Let's just go through the process with just b and c as 1. I could add them together. Derivative is negative e negative x plus negative 3, negative 3x prime equals e negative x plus 9e negative 3x. I can plug these in here. Well, we already know this sum is going to be 0. This is the solution. We know this sum is going to be 0, because this is a solution. So the whole thing is a solution. For that matter, any numbers A and B I can plug in here, make it a solution. Even A and B 0 makes it a solution, right? X, Y 0, its derivative is 0, its second derivative is 0. And that works. So what does that sound like? I've got these objects. I can multiply them together. I mean, I can multiply them by a constant. I can add them together. And they all work. Right? Does that sound like something we talked about? It sounds a little like a vector space. Oh, wait, it's not a pointing arrow. This thing, it's a solution. We've got this world of solutions defined by these two constants and these two solutions. So I bring this up not because I expect you to spew this back. I just, this is the next layer of math that is just above you. It's all within your grasp. And I find it really interesting that here, you could take a whole course on this here, and they never mention a vector space. You could take a whole course on linear algebra, and they'll never mention a differential equation. But lo and behold, you have this beautiful connection here that anything we find out about in linear algebra about vector spaces, we can apply to these differential equations. And maybe vice versa, to check. So, all right, I just wanted to throw some ideas around in case maybe some of you will catch the bug. You may come across some of this anyway in your studies as part of prereqs. You may need this, but all right. That's all I got. Any questions or have a question? No. All right. Well, have a good afternoon. Come up with something for Thursday, and then we're almost done. What is it? Paper, like PhD paper, beat spot or something. Yes, okay. Oh, is that it?
No, there's more. It's just
Okay.
I don't know how to do it.
That's not what I meant.
Oh.
Do you have more you want to ask?
Oh, are you free for office hours?
Yeah, I'm going down there as soon as I'm done here.
Oh.
You're coming, I take it.
I missed out on this part. It's like for this one, graph, should I use g of x minus f of x or f of x minus g of x?
Well, you subtract g of x from f of x because it's below.
Oh, so
Or you cheat, you just say absolute value, and if it turns out negative, you switch.
wait, so like for this one, it's like this equation is like above this one. You use this one subtract by this one. Or like
You do the same thing down here.
oh, but like if it's like below the x-axis, like this one is way below this one, then you can use this one subtract.
No,
No.
no. You still subtract this one from this one. Because moving up and down doesn't change the value
So it's
of the
like-
integral.
It's just like that.
That's the point here is the c's cancel. So you can move the axis wherever you want. The area between them stays the
Alright,
same.
so is that correct?
Yes.
Alright. Wait, so when do I have to use the absolute?
You have to use that.
When like the curve
Well,
overlap?
Okay, if you have a curve that's like this, and I want, from here to here, right? So this is positive, and this is negative. Now, you could do the same thing we're doing here. You could say, you have to break it up anyway. So from here to here, it's positive. From here to here, we'll call this area 1, area 2, area 3. So it's area 1 minus area 2 plus area 3, right, to make this positive. Let's see. That's,
Oh, I see. Yeah. Okay. Thank you.
yeah. You know, I hadn't thought of it until you just came and said, well, we're talking about the area between two curves. The x-axis is a curve, so we can just eliminate thinking about that and just think of it as the area between two curves.
All right. Okay.
Yeah. All right. Lillian, did I mix up your name earlier? Did I call you Emily?
Oh, I was confused. I thought you were like, wait, I think so.
I'm sorry. I
Oh,
apologize.
wait, Emily's here? When I heard Emily.
I don't think she's here.
She's not here.
Or,
I heard that she was very bad.
you heard it, what?
That Emily was very bad.
She's had a rough time this semester. You know that. Is it? There's no name on
It's mine.
it. This is yours?
The messy handwriting I saw.
I'm asking every day
Oh.
in class.
Oh, really?
No,
I didn't.
not every day,
Oh,
but I asked a few times.
oh, I didn't hear.
And why did I write Emily? Because I guess, I don't know, those names aren't the same, not even remotely. Okay, I have to, this is special, this goes, because I give you credit for it.
I didn't even see what it was, but I saw that
It won't make any
messages.
difference.
And then I saw the messages.
It's
Oh
not
my God,
gonna
that's
hurt,
my.
it's not gonna hurt you.
It looks really bad.
It looks bad,
Yeah, why is this so messy?
but messy doesn't matter in math, as long as, oh, wait a minute, I just had a bunch of, where did I just put the file? Oh, there they are. Oh, that doesn't go there, this goes there, okay. See? With great care, it doesn't look that way, but
Oh no, I mean,
I go home and
I wouldn't
I
know.
need computers to help.
I wouldn't know how to organize so many students.
Oh, neither did I, until, you know, it really makes you good at that part of teaching, really gets you ready to teach high school. Woo!
Oh, you taught high school before?
I taught high school, yes,
Oh, how was that?
dreadful. I mean, the students, I like the students. Here, you know, there's some issues with the administration, but they're minor compared with high school. To me, the most evil people go into administration of public schools. Oh, wait. No. Ready up, see. System off. Okay, you just pick up the camera. You do know that the last day of class, which is a week from today, is dedicated to